Welcome to question 1 of the 2019 Mathematical Methods Exam 1 for the Southern Hemisphere. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAR. For question 1 we let f be the function with a domain of 1/3 to infinity, where f of x has a rule of 1 divided by 3x subtract 1. For part 1 of part A we're asked to find f dashed of x, which is the derivative of f. So if we have a look at this function, we're going to need either the chain rule or the quotient rule to differentiate this. So for me, I think the chain rule is going to be easiest to apply. So in setting up the chain rule, I'm going to let y equal 1 divided by u, where u is just the function on the bottom line. And that could also be expressed as u to the power of -1. If y equals u to the power of -1, then u was the bottom line, as we discussed before, which must be 3x subtract 1. Next we want to work out what the derivative is, that is dy du. So that's going to equal -u to the power of -2. And du dx, which is the other derivative that we need to find, is going to be 3x take 1 derives to be just 3. Next, if you look at your formula sheet, you'll find that dy dx is dy du times du dx. So that's the chain rule for differentiation. So therefore, f dashed of x, deriving f using the chain rule, is going to equal dy du, which is -u to the power of -2. The -2 just means that we're going to have u squared on the bottom line of this fraction, so we're still going to have the negative, so I can write that as -1 divided by u squared, which is 3x take 1 squared. And then we take that value and then we multiply it by du dx, which is simply 3. And we can simplify that slightly, as multiplying the first fraction by 3 will just give -3 divided by 3x subtract 1 squared. So that will be the answer to that part of this question. For part 2 of part A, we want to find an antiderivative of f of x. So the word "and" means that we don't need to worry about the plus c value. We can just choose c to equal 0. So to find an antiderivative of f, I'm first of all just going to set up the statement. So what we're really being asked to find is the antiderivative of 1 divided by 3x subtract 1 dx. So there's a couple of ways of working out exactly what this will turn into when we've anti-derived it. The first way that I like to think about is I like to just set up an integral with the bottom line. And the bottom line is 3x subtract 1. And then I consider what is the derivative of 3x subtract 1. In other words, what's the derivative of the bottom line? And that would simply be 3. However, I can't put a 3 on the top line without balancing that out in some way. So if I've multiplied this expression by 3, to balance that, I'm also going to divide by 3, or multiply out the front by 1/3. And then that integration is happening with respect to x still, so I need to remember that dx there in my working. So now I do have a case where the derivative of the bottom of the fraction is sitting on the top of the fraction. So that's going to indicate that we are going to a log. So this will become, we'll still have the 1/3 from out the front, but now we will have log e of the bottom line of this fraction, which is 3x subtract 1. And then, as we discussed before, because it's an antiderivative, I don't need the plus c, or you could choose to put any plus c value there that you like, but that is a suitable answer for this question. So before we move on, I'm just going to show an alternate way that you could have tackled that problem. So it's going to look similar to start with, that we're going to start with an integral, and we're going to pull a factor of 1/3 out, because that's the coefficient of x on the bottom line. So we're going to remove that from this statement. And then we're going to have 1 divided by, and because we've removed a factor of 3 from the bottom line, that's what the 1/3 out the front is doing, we're just going to be left with x, and then instead of subtract 1, we'd have to have subtract 1/3 there, and that's integrated with respect to x still. So if you expanded that back through, you'd get the same expression as what we started with, and that just means from this form, we can go to our log answer as well. So this would equal 1/3, which is the value that's out the front of the integral, stays out the front, times log e, and then inside the brackets here we'd have x subtract 1/3. So it turns out that these two things are essentially equal once you consider the fact that they would have different plus c values. So if you were trying to find a unique antiderivative, they would have different plus c values. But for this question, it's just find an antiderivative, so either of those answers would be accepted. So from the examiner's report, we can see the majority of students correctly applied the chain rule for the first question. And the examiner's report goes on to say that the errors that were made by students, and as we can see, only 67% of students got this fully correct, those errors were generally to do with their arithmetic or to do with dealing with that negative exponent. So the -1 on u that we discussed on the previous slide. For the second part of that question, we can see that it's not overly well done for the first question on the paper, with only 50% of students getting the mark for that question. The examiners noted that there were various ways of expressing the antiderivative, with the above two being the most common correct answers. And the most common error that students were making was placing a constant of 3 or 1 out the front of the log expression instead of a third. And the tip that the examiner's report gives is that students should know they could easily verify their answer by using the chain rule to differentiate their answer and checking whether or not that was a derivative for the rule of f. So if you did have time in an exam situation, that's one way that you could check an answer to that sort of question. For part B of question 1, we are introduced to the function g, which has a domain of all real numbers excluding -1. And the rule for g of x is sine of pi x divided by x plus 1, and our job is to evaluate g dashed of 1. So to tackle this problem, we're going to need to use the quotient rule, because we can see a function divided by another function. And to set up the quotient rule, we're going to let u equal the function on the top line of the fraction, which is sine of pi x, and v is going to be the function that's on the bottom of the fraction, which is x plus 1. We then need to find du dx. So sine of pi x, if you look at your formula sheet, will go to pi cos of pi x. And dv dx, the other derivative that we'll need to complete this problem, is the derivative of x plus 1, which is simply 1. Also on your formula sheet is the derivative of the function u divided by v, which is the quotient rule. So that rule states that for a function u divided by v, the derivative is simply going to be v times du dx minus u times dv dx, all divided by v squared. So our job is just to apply that rule now. So we're going to have g dashed of x, because that's the function's name in this question, is equal to, and v is x plus 1 times du dx, which is going to be pi cos of pi x. And then we're going to subtract away from that u, which is sine of pi x, times dv dx, which is simply 1. And all of that needs to be divided by v squared, which is x plus 1 squared. However, we're not done yet, because the question asks for the derivative with 1 substituted into it, or g dashed of 1. So therefore, g dashed of 1, we just replace any x with 1. So x plus 1 here becomes 1 plus 1. Then we'd have that being multiplied by pi cos of pi x. So that's just going to be pi times 1. Minus sine of pi times 1, which is just sine of pi. And then we divide that by x plus 1 squared, which is going to be 1 plus 1 squared. And then we just look to simplify this as much as possible. So cos of pi, the exact value for that is -1. And sine of pi has an exact value of 0. So therefore, g dashed of 1 is going to equal 1 plus 1 is 2 times -1, and we've also got a pi in there that we can't forget about. So this becomes -2 pi, and then we just subtract away from that 0, because that's what sine of pi was equal to, and that is divided by 1 plus 1 squared, so 2 squared is 4. So that fraction can be simplified a little bit further. So we find that g dashed of 1, which is what this question was asking for, is equal to minus 2 pi divided by 4, which is just -pi on 2 when we cancel a common factor. So that is the answer to part B of this question. From the examiner's report, we can see that 50% of students got full marks for this question, with almost 40% of students getting 1 mark. The examiners noted that though the question was generally well handled, poor placement or lack of brackets when using the quotient rule or for some students, a combination of the product rule and chain rules, led to errors in evaluation. So I can't stress enough the importance of placing all of those brackets in the setup of that question. Other errors included the misconception that cos of pi equals 1, which we know cos of pi equals -1, or sometimes it was misquoting the relevant differentiation rule. And the note here is that those differentiation rules are listed on the formula sheet for this exam, so you should refer to those when you're doing these problems just so you don't get it wrong. Another thing that stopped students from getting full marks on this question was not answering the question in its entirety. So the important thing here was that the answer that was required to be found was g'(1). And what I imagine happened for a lot of students that got 1 mark is they stopped at this point, having found g'(x), and forgot to actually find g'(1), which is what the question asked for.